Test.
Hello, can you hear me?
Yes, okay, it works for me too. Awesome.
Great, I can hear you as well. So I guess, can you see the slides I'm sharing?
I can see them, yeah.
Okay, great.
Yeah,
so I guess we're on time.
You both can see the slides.
Great, hi Colin. So I guess we can start, right?
Yeah, let's start. I think we're on time.
So just FYI, some people are telling me they cannot join the Meet Echo with the IETF registration code. So I don't know if that's a bug or a feature.
People need to register for this workshop separately, but if they have an IETF registration code, they should go to the site and do it for free straight away.
Okay. I'll try to pass. Sorry, yeah, I was just saying I'll try to pass the message along. But okay, well, hopefully a few people have joined, so they have managed to find their way. So I guess we can start for today. The first session of the introduction and welcome. So my name is Anrw. I'm a researcher with Telefonica, and this year, well, we together with Nick, we were entrusted with taking care of the technical program for the Applied Networking Research Workshop. So thank you very much to the steering committee, and thank you, Colin, for giving us this wonderful task. We have had lots of fun. So we'll discuss a little bit about the process and how the program looks like, what we have in store for you. So thank you everybody for joining today, and we hope you're gonna enjoy it. So I don't know, Nick, if you want to say hi.
Oh, sure. I'll just introduce myself, and thanks, Anrw, for kicking it off. Hi, everyone. My name is Nick Feimster. I'm a professor at the University of Chicago in Computer Science Department, and I think we're very excited to present the program to you. Anrw, I don't know if you wanted me to talk about IETF now or later on.
Yeah, I mean, I just wanted to say, like, the first task we kind of got, when we set out to put together the program. Obviously, we got a lot of our friends together in the technical program committee. A lot of our, a lot of the people who support the Applied Networking Research Workshop. So we couldn't have done it without the program committee. So we obviously, huge thanks to all the 30 people who have helped us in this effort. So you see them all here. And I think, as you've seen, we put a lot of, effort into making sure that the reviews are mindful, constructive, and, useful for the people who have submitted. So 3 of the people we have invited to the technical program committee actually have helped us with this. So I know Nick has much more to say about this initiative.
Oh, yeah, I'll just say a couple words. I mean, I think one of the things that we wanted to do is ensure that the people who submitted papers got reviews of a quality that they were happy with. And so Anrw and I tried very hard to maintain high quality on the reviews. And as part of that, we asked 3 of our senior members of our community here to serve on a review task force, which helped us oversee the review process, essentially reviewing the reviews, looking and make sure those reviews were responsive to technical concerns in the paper, that they were substantive, and that if they made critical suggestions, that they were backed up with concrete feedback and actions that the authors could take to improve the papers. And I think in addition to that, I think Anrw and I spent a lot of time ourselves. We're probably members 4 and 5 of the review task force, really going through a lot of the reviews, making sure that everything was handled with care and with thought. And I think some of the authors, I hope appreciated that as well, because I think we did go back and review the reviews, including taking some appeals, which doesn't always happen in conferences. But we hope that this can help set the tone for the future, for the kind of event that ANRW can be, a place where people can submit all kinds of applied networking work and expect to get constructive feedback on the work that they present.
So yeah, I couldn't agree more. So thank you again so much to the task force, and not only that, but they also helped us link very well the submissions with current interest that the IETF and the RTF have. So hopefully everybody here will find the program exciting. And I just wanted to bring to your attention that a lot of these papers that you're going to hear about during these 3 days of workshop, they have different artifacts attached to them. So hopefully contributions that are going to be useful for the community. And obviously, we would like to thank the sponsors for supporting and for making sure that everybody can attend the workshop. Just a little bit of boring details. So as you know, we are virtual because of the world today. So thank you so much for putting the effort to join, even if in this current conditions and in this format. We do have a Slack channel where we encourage you to go and interact with other people who might be presenting or continue conversations you might have here. There is also the gather space. So in the floor plan, just if you roam around, you're gonna find us somewhere. So you can definitely also join there for coffee breaks and so on. All the program and details, you can find them online on the NRW website. The proceedings are also live. Just note that all the sessions are recorded, and I'm going to bore you a little bit with some more information. The note will on the intellectual property just does not apply for contributions that were made for the Applied Networking Research Workshop, so we just wanted to mention that. However, do please observe the note will on audio and video recordings. Essentially, if you participate online and if you turn on your camera and on your microphone, you essentially consent to recordings that we might do. As I mentioned before, all the sessions essentially are going to be recorded, and we're going to add them to our YouTube channel, to the workshop's YouTube channel. And also please observe the note will on privacy and code of conduct. Essentially just, agree to work respectfully with the other participants. Just a few notes on ITECO. So as I mentioned before, we are going to run all the workshop essentially here. Presentations are pre-recorded. You can actually go and preview them on the program website, on the workshop program website. Each paper basically gets 10 minutes of presentation, and then it's followed by a 5 minutes Q&A. And at the end of each session, we will have also a 15 minutes panel where we basically want to encourage you, all the attendees, to engage with the authors in a more lively Q&A session. If you would like to ask questions, we encourage you to use the Meet Echo queue, the virtual queue that each of the session chairs is going to handle. So I'm sure that if you need more information, as you can see, we have support here. Both Nick and I will be here in order to make sure that things run smoothly. And if anybody needs help, yeah, just let us know. Would you like Nick to give an overview of the program, how we schedule it, or?
Sure. Sure. So we organize the papers into thematically into 6 sessions, and we'll meet 3 times over the next 3 days for about 2 hours, and each session has 2 themes. Today we'll hear about internet protocols and congestion control, and the subsequent slides have papers on each of these, so we can just look at those in a second. But then tomorrow we'll have interconnection and routing and internet traffic monitoring, and then on Wednesday we'll talk about DNS and privacy, and then applications. We also tried to clump the 2 themes, so that they would be reasonably related, so that if you could only attend on one day, hopefully you're getting what you came for. Great.
Yeah.
So should we go over the papers in each session, or?
Yeah, I just wanted to add that overall, I think we received about 28 submissions. So thank you so much, everybody who submitted. And thank you for your interest. And, based on the review process we put together, we ended up accepting about 16 papers, which we basically try to put in these sessions. So it's a pretty, deterministic program. So it's always 2 hours from Monday to Wednesday. We're going to meet at 7 p.m. UTC in these 2-hour slots. You can see that each session has a session chair assigned, and we're going to just hand over today directly for the new session on internet protocols. We have 3 citing papers from 3 speakers, as I mentioned before. Just keep in mind that, each of the talks will be 10 minutes, followed by a very short Q&A immediately after. And then, to give you a bit of time to just, think of your questions and engage with the authors, we will have the 15 minutes panels that each of the session chairs is going to basically manage. So today, as Nick was saying, we have the new internet protocols with 3 papers, followed by practical congestion control with 2 papers. So hopefully the slot that we have assigned it fits perfectly. Today, Anna Brunstrom and Teresa Einhardt are going to help us session the 2 chairs. Tomorrow we're going to have the session on interconnection and routing, and here Amrish is going to help us chair the session with 2 talks. And then session 4, which is a longer session, here we're going to have 4 different talks, and then Mundo is going to help us chair this session. In the last day, we have DNS and privacy, which Nick is going to take care of. And I'm going to be with you right till the end with applications and specifications. So this is it for me, right on time. Again, huge thank you to everyone who submitted. Congratulations to the authors. Thank you so much to the PC. We literally could not have done this without you. And again, massive thank you to Colin for all the support, like with everything on all aspects across all this process. So thank you so much. And again, thank you to the steering committee for trusting us to put together this program that we hope at least you will enjoy. So that's it from me.
I think you said it all. I have nothing to add, except I'll add my own thank you to again to Colin, especially for shepherding us through the process of getting the program put together and organized, as well as to our program committee, who did a lot of hard work. And also, I'll thank you, Anrw, as well, for handling some of the trickier logistics, as well as getting everything on the website, among many other things. So thanks a lot.
No, thank you. I mean, it's been great. And again, thanks so much to all the support staff who have helped us schedule everything and have bared with us, because some of us are new here. So thank you so much for everything, and we do hope you will enjoy this. So we'll be here, but now I think I'm just gonna hand over to Anna. So I'm just gonna maybe just go to session 1 here. And I think we can already start our first session.
Yeah, over to Anna. Thanks.
And thank you so much, Anna, for helping us.
Thanks so
sure.
much.
Thanks, Anrw and Nick. So I'm Anna Brunström from Karlstad University in Sweden, and I have the pleasure of sharing this first session on new internet protocols. And I think we have 3 very interesting presentations to look forward to, as you see on the slide here from Anrw. So I think we will jump right into it. And the first presentation is given by Markus Pieska. And Markus is a PhD student at Karlstad University in Sweden, and his research focuses on transport layer congestion control and multipath scheduling in the context of wireless communication. And he will be talking about adaptive cheapest path first scheduling in a transport layer multipath tunnel context. So I will ask Mitiko to start the first video, please. And you can put in your questions and join the queue while the video is playing.
Hello, my name is Markus Pieska. I work as a PhD student at Karlstad University in Sweden, and I'm going to present to you the outcome of work done on multipath scheduling in the context of multipath transport layer tunneling. This presentation is organized into 3 parts. The first will introduce you to the main motivation for this work, which is the planned built-in multipath support in 5G. Secondly, I will present the multipath packet scheduler we have been working with and the issue we have found with it. Lastly, you will see the modifications made to this scheduler and the performance improvements they enable. But first, let's begin with the multipath support in 5G networks. This multipath architecture goes by the name of Access Traffic Steering, Switching and Splitting, or ATSSS, and is supposed to offer transparent multipath support. This multipath framework would allow for the simultaneous usage of cellular networks with other wireless access, such as Wi-Fi. For TCP, the idea is to enable this by splitting the end-to-end TCP into regular TCP between the server and a proxy, and multipath TCP between that proxy and a user. For non-TCP traffic, a transport layer multipath tunnel may be used instead. The latter case is, of course, the focus of our work and this presentation, and we use this topology to illustrate a typical scenario. So assuming downlink traffic, data originate at a server, possibly using a transport layer protocol that support congestion control, such as, for instance, QUIC, regardless of if it's reliable or unreliable. Data then arrives at the previously mentioned proxy, where it is passed into our multipath tunnel and encapsulated, with each path then having its own congestion control. The data is then scheduled over multiple paths based on the state of the congestion control of those paths, as well as other path information that may be obtained from the corresponding transport layer instance. This may seem straightforward enough, but the existence of nested congestion control loops and the interaction between these and the multipath scheduler can and do cause problems that need to be addressed. That brings us to the second part of this presentation, where I describe the particular scheduler we have been working with. Since ATSSS would allow for the usage of Wi-Fi alongside the cellular access, a scheduler that is able to express a preference for the cheaper Wi-Fi becomes attractive. This is true for users as well as telecom operators, both of whom may reduce costs by offloading traffic onto the Wi-Fi whenever possible. One scheduler designed to deliver traffic distribution in this manner is the cheapest path first scheduler. The basic idea behind this is to rank order the paths by cost in ascending order and to schedule packets over the cheapest path until the amount of in-flight data match the size of the congestion window, at which point the scheduler instead attempts to schedule packets over the subsequent path. The problem with this is how first is defined. If first means until the congestion window is full, as I previously stated, it will tend to lead to a full utilization of the primary path, which is what we want, but also to congestion, which is troublesome for more reasons than just the increased delay. As it turns out, the congestion will also delay or completely preclude the utilization of the secondary path. The extent to which this is a problem will depend on the potential for congestion on the primary path. Basically, anything that reduces congestion on the primary path has the potential to alleviate this problem. A simple example will hopefully illustrate the issue. In this case, we are running a user space multipath tunnel with each individual path being managed by a TCP instance in the Linux kernel. The topology previously shown is set up in Minet with the capacity of each path being 50 megabits per second and with a moderate delay asymmetry. A download is initiated using a greedy TCP application. Thus, in this case, we tunnel TCP New Reno over TCP BBR, as it offers an easy analysis. Finally, we have a first in, first out queue at the bottleneck, which is large enough to hold the congestion window that BBR will tend to output. Please also note that the throughput in these plots are stacked, and that we therefore would like to see the throughput reach the 100 megabits per second line. The event highlighted here is a reduction in the server congestion window, which is expected from time to time as it's part of the normal congestion control cycle for TCP New Reno. This in turn is followed by a reduction in throughput. This may seem in order, but it's actually quite bad, as seen when taking a closer look at the state of the network. After the event shown in the previous slide, the primary path is likely at least somewhat congested, while the secondary path is unused. If we treat the two paths as a single path for the purposes of analysis, we have both congestion and underutilization, which is something that you do not expect to see at the same time. This is obviously a malign state and can be thought of as kind of a bad distribution of the server congestion window over these two paths. So this brings us to the third and final part, where I show you the modifications made to this scheduler to overcome this problem. The basic idea is to redistribute the server congestion window to maximize the throughput. The first step is to determine the bandwidth delay product of the primary path, with the delay in this case being the minimum delay. We then introduce what we call a live congestion window, which is a fraction of the full window, ranging from the BDP to the full window. The scheduler is then changed to act on the live congestion window instead of the full congestion window. Finally, we manage the live congestion window by periodically increasing it if there are packets in the scheduling queue and decreasing it otherwise. Returning to the example shown previously and using the same configuration except for the new scheduler, we see that we no longer have a problem with the utilization of the secondary path. However, we still see periodic reductions in the server congestion window, So why then is the throughput so good? The answer is that the scheduler compensates for the smaller congestion window, which it infers from the scheduling queue size, by reducing the live congestion window. The net effect of this adjustment is that the server congestion window pivots from the bottleneck buffer of the primary path, where it was causing congestion, to in-flight over the secondary path, where it instead increases the throughput. One may conclude from this simple example that the improved scheduler is able to maintain full utilization by departing from the behavior of default CPF when necessary. Although one cannot be certain from these plots alone, it is a good guess that the utilization of the secondary path would have been poor after the highlighted event had standard CPF been used. A more detailed evaluation is available in the paper. In it, we look at multiple end-to-end congestion control algorithms, multiple topologies, and different tunnel protocols. Regardless of the configuration used, the default CPF scheduler exhibits the same issue, which is subsequently solved by our modification, again, regardless of the configuration. Future work will include a better integration with the BBR tunnel, whereby the BDP can be learned from the BBR state as opposed to just inferred. This is actually critical, as this scheduler will misbehave if it uses a bad estimation of the BDP, and in particular, the split flows needlessly if the BDP is underestimated. We are also evaluating this in a switching scenario as opposed to the splitting scenario illustrated here. That concludes this presentation. Thank you for your attention.
Okay, thank you, Marcus, for that video presentation. And let's see if we have anyone in the queue for questions. I think, Marcus, you can also turn on your camera so that we can see you for the Q&A session. So we have now a short opportunity for questions, and then we will also have the larger discussion at the end. So I don't see anyone in the queue right now, but maybe I can ask, you mentioned here that you have experimented with different congestion controls. Could you say something about how the different congestion controls impacts this problem that you are looking at?
Sure. Can you hear me all?
Yes,
Yeah.
we hear you well.
So if you mean by that the end-to-end congestion control, one interesting aspect is if you use something more traditional, like let's say Neurino, then you get a cheapest path first scheduler that works only intermittently. So it becomes sort of unstable. Whereas if you use BBR end-to-end, then you get a cheapest path first scheduler, if it's tunneling over BBR, that either works or doesn't, but it's stable. So how this misbehaves will vary depending on the combination of congestion controls, but it will misbehave, the default scheduler. But it takes it varies between combinations.
And some combinations are worse than others, or?
Yeah, it depends on what you want, I guess. If you're unlucky and the configuration of your network is a certain way, let's say, then getting aggregation with BBR over BBR is just hopeless. It will never happen. Whereas, regardless of the configuration almost, if you have, let's say, Neurino or Cubic over BBR, then you will get aggregation intermittently. So it depends on what you want, but it's certainly a bit discouraging to see that the consistency with which BBR over BBR misbehaves sometimes. It just refuses to show any aggregation of the path capacities.
Okay, thank you. I see we have Spencer in the queue. Please, Spencer, unmute yourself and ask your question.
Hi. I wanted to thank you for your presentation, and I just wanted to, this is something that actually is kind of interesting to maybe more people than I had previously thought at the IETF, including myself. I was wondering if you had had an opportunity to think about a broader range of path characteristics, like including satellite and things like that, which are, that's starting to show up in the 3G PGP specifications for, I guess, phase 2 ATSSS, really 17 kinds of things right now. So that there is a real range of things. And I'm also, and this is probably more speculative, I'm not talking about 3GPP futures here, but the idea that you may have 3 or more paths rather than the 2 paths that ATSSS is defined to use right now. My question is kind of probably about generalizing your findings to things that are not particularly ATSSS specific. And I'll stop asking questions now.
Yeah, I think you will see the same problem to begin with your last question, even if it's not a tunnel. So if it's end to end, I suspect you may see the same problem. So in that case, in that sense, I guess it's generalizable. About more broad scenarios, that's certainly something that we're doing for a follow-up, including one where we are looking at. In this case, it's just we have a greedy flow, so we want to have aggregation all the time. That's a sort of easy test to put this scheduler to. A much more challenging one is where you have a rate limited flow that will need aggregation occasionally when the Wi-Fi is particularly bad. And these are the kinds of things that we're looking into right now to see if it behaves well done, including having more dynamic channels. Because in this paper, we have only stable channels with a constant bit rate.
Yeah, sure.
Once it's more stable, it's very tricky to get this to work. Or more unstable.
Like I say, I'll mute and let progress happen. But this is stuff I'm really interested in talking with you all about more. Thank you.
Okay, thank you, Marcus and Spencer. I think we should move on to the next presentation, and you can also save up if you have more questions for Marcus. We will be back at the last panel for all the papers, so you still have a chance if you think about some more questions. But let's move to the next talk, which will be by Mathieu Bertz. And Mathieu is a software architect in the R&D department at Thesaurus, which is a spin-off from UC Louvain in Belgium. And his research interests are around multipath technologies like multipath TCP and multipath QUIC. And he is also currently co-maintaining the MPTCP stack in Linux. And Mathieu will be talking about leveraging the zero RTT convert protocol to improve Wi-Fi cellular convergence. So let's first see the video. So please, Metako.
Hello, and welcome to this presentation about leveraging the zero RTT convert protocol to improve Wi-Fi and cellular convergence. Behind this long title, there is an experiment I would like to describe. But first, I will start by describing why we wanted to do this experiment, simply by showing the current and future situation. I will also present which technologies are available today to solve the problem. Then I will be able to briefly expose the main results we got before making some conclusions. For technical reasons, it is not possible for me to know the background of the audience. I hope you don't mind if I spend a bit more time explaining the current situations, issues mobile operators have, and the different technologies available today to solve that. Feel free to get a coffee if you already know all of that, but at least, and I hope, everybody should be able to understand the second part. It is not difficult to believe the traffic on cellular networks is increasing. According to this report from Ericsson, it will continue to grow over the years. Already today, the cellular traffic is significant. For a third of the operators here on the graph, the average data usage per reported SIM per month is already above 10 gig. A simple solution to cope with this increase of traffic for the operator is to improve the network, to avoid any saturation, of course. Yes, but the average revenue of these operators is not growing. Despite the pandemic we got, I don't know if you remember, people were forced to stay home to save the world. Anyway, despite the exceptional situation in 2020, the global cellular traffic this year increased, but not the revenue. If we have to reduce the cost, then another solution is to use the existing fixed infrastructure. Indeed, millions of Wi-Fi hotspots are already available in many different places. You might have heard about solutions like Phone or EduRoam, or simply your operator's hotspot, also called free Wi-Fi. Many operators have already deployed their own hotspot solution just for their clients. But today, the Wireless Broadband Alliance, supported by many different network operators in the world, is looking at a global solution under the name of open roaming. Operators would share resources in order to relieve cellular traffic congestion. But there are drawbacks. As an end user, would you be ready to be disconnected when switching from one network to another, or potentially switch to more limited networks? Did you not already disconnect your device from a Wi-Fi access point because the cellular network was better at that time? A solution to that problem would then be to use multiple networks at the same time. Multipass TCP can help you there. MPTCP is an extension to TCP, and it's standardized in the RFC 8684. To describe MPTCP, we can do that in one sentence. It allows to exchange data for a single connection over different paths simultaneously or not. Instead of having one connection limited to one path, the same connection can go over multiple paths. In other words, you can then have more redundancies, but you can also have more bandwidth and more menacing, like supporting handover and mobility use case, like here switching from one weak network to another, where all the signals are quite valuable. But this extension to TCP needs to be supported by both the client and the server. On the client side, some smartphones already support it, like the one from Apple since 2013, but also some others from Samsung, LG, and more, even if it's restricted to some applications. As shown on the MPTCP.io website, on the server side, the support is not very significant for the moment. For various reasons, we are actively working on it. But wait, again, there is a solution. A TCP proxy can be used at operators' network to bring MPTCP support. But what kind of proxy should we use? Here we are interested by a new protocol, Zero RTT TCP Convert Protocol. It eases the deployment of TCP extensions like MPTCP. Technically, it uses TCP fast open, with fallback support of course, to carry information about the end server. Note that the client and server proxies can exchange additional data in the three-way handshake, for example, to support an additional authentication part. If we compare the flow to initiate the connection, it is a lot shorter than solutions like SOX V5 used in Korea with their Giga LTE. In the end, all the solution I presented here, combining MPTCP with the Zero RTT convert, is already part of the future 5G. Indeed, in the 3GPP release 16, an ATSSS function is defined. ATSSS stands for Access Traffic Steering, Switching, Splitting, and it combines all two technologies to play a key role in managing data traffic between 3GPP, so 5G, 4G, and those networks, and non-3GPP networks like Wi-Fi or private networks. Enough with the introduction. Let's have a look at our experiments and at the main result we extracted from them. From a high-level viewpoint, we have a smartphone connected to two networks. The first one is a DSL network connected via Wi-Fi. It is a home network, unfortunately limited to 10 meg. I said unfortunately because it is my home connection. The other network is a public LTE network, giving more than 20 gig, but it is variable. A zero-RTT convo server is deployed on the internet, and the phone is simply playing live video stream from Twitch. Specifically, the smartphone is a Xiaomi Pocophone F1 with a modified kernel to have MPTCP support. A modified version of Shadowsock supporting the zero-RTT TCP convert protocol is installed. Please note that all the material has been open source, and a nice guide is available on Tessera's website. For the TCP proxy server side, we took a server called HAG, used for hybrid networks. It follows broadband forum standards and supports 10,000 of users with 10 of gig of throughput and 300,000 connections per server. Of course, here it has been modified to support the zero-RTT convert protocol. For this experiment, it has been deployed in the cloud close by at Amazon. Regarding the results, we can focus here on two scenarios. For the first one, the goal is to support handovers. Here, we are disconnected from the Wi-Fi access point between the two green lines. When we are connected to the fixed network and the Wi-Fi, we use it in priority. Here, the DSL network can cope with the requested speed, so the traffic is fully offloaded to the fixed network. Excellent for the operators. Here, in the second scenario, the DSL network is not enough to watch a 4K live stream. We can clearly see on the graph, before and after the green lines, that the cellular network is used in a second priority. The main point here is that it is used in addition to provide enough bandwidth to play the 4K live stream without delays. It then helps to improve the user experience while still minimizing its utilization. So that's good for the end user. It is already time for conclusion. This proof of concept shows that the future ATSSS already works. On one hand, it helps mobile operators to reduce their mobile traffic while also helping to improve the end user experience. MPTCP and the zero-RTT convert can play a role in Wi-Fi and cellular convergence today in 4G networks, and tomorrow in all 5G networks thanks to the ATSSS. Thank you for watching. If you have any questions, please share that with me, but you can also contact me by email or Twitter on others. Thank you.
Okay, thank you, Matthew, for that video presentation. I think you can also turn on your camera. Great. And we have the queue open if we have some first quick questions for Matthew. So maybe I can start by asking, you're using the TCP fast open. How have you seen the support for this? I know that maybe not all the servers will support this. Have you experienced how frequently this works and how often you have to fall back? Or we don't hear you.
Is it still better now?
Now we hear you, yes.
Sorry, my bad. Yeah, so yes, for TCP fast open here we are quite fine because we use it only between the smartphone and the HAG, so the server that we set up in the network operator. So we only have to ensure that TCP fast open cannot be blocked on the network side. But typically it is used not a private network, but I mean a network that is controlled by the operator. So it's the operator deploying the server. So I hope that the operators can also make sure that TCP fast open is not blocked in the network. But we are not using TCP fast open to reach the end server, so the one on the internet. So we should be only able to use TCP fast open between the client, which should be on the operator's network, and the server that is in the operator network. Hope it's clear.
Mm-hmm. Okay, yeah, so this of course makes it, yeah, reduces the problem, I guess, yeah. I noticed in your graphs when you moved to the LTE network, you had quite a bit of fluctuations. Was this effect of the measurement techniques or scheduling, or it looked fairly regular, but I don't know if it was just natural fluctuations or some effect of your setup.
So we looked a bit, especially after the review that we got, and what we saw is that it seems that the end server, so it's Twitch, so it's a live stream video, was able to push more data on the LTE network. And because I'm quite lucky to have a quite poor DSL connection, we can see that it's quite stable, everything is good. But also because I'm on the countryside, the LTE is sometimes better, but also fluctuating. So if we combine both the server that is able to push more data quickly and the LTE network that is a bit variable, that's why we were able to see more variance there.
Okay. Okay, I see we have Tianjai in the queue, so please unmute yourself and ask your question.
Hello? Hello?
Hello?
Can you hear me? Yeah, can you hear me? Okay. Yeah, I have a question regarding for the DNS part. For the UE, sometimes it's going to, by default, the UE is going to get a DNS service from the mobile provider. But sometimes the UE can set its own DNS in its own way. So here, if you have both ways, like through Wi-Fi, non-3GPP case and the 3GPP case, so if the UE does specify the DNS in his own way, how are you going to do this type of convergence? It's like a switch over between the non-3GPP and the 3GPP ways. Thank you.
Yes, I hope I understood the question properly. So if I may just quickly repeat, so I think the question is about what if there is a custom DNS that may be forced to take one path or another?
Yeah, this is like a feature where you can change on your UE. But for a mobile provider, they default, they prefer to use the DNS provided by the mobile provider itself. But here you have a non-3GPP path like a Wi-Fi. So the Wi-Fi will have its own DNS. So now you have three ways. One, DNS provided by mobile provider. One provided by the non-3GPP like a Wi-Fi. And the third way can be manually set by the UE itself. So now, how are you going to do this type of the switching if the UE, prefer to do something by itself? Yeah, thank you.
Okay, yes, thank you. It's clear now. So here, what we technically do is that when the UE is requesting to go on a website, we catch the connection and we send it to our proxy server, so the HAG proxy server. And what we put in the information to connect to the end server is its IP. So at the end, what we have is that the UE do the DNS request. It gets an IP for the end server, and that's this one that is going to be used by the HAG server in the network operator to reach the end server. But then it doesn't matter if you are using Wi-Fi or LTE, because all it matters is that it's the IP that is provided to the hack to contact the end server. Does it answer your question?
I think I understand. Okay, thank you.
Okay, thank you, Mathieu and Oscar for your questions. I think we move to the next talk, and Mathieu will also be back for the panel at the end if you have more questions for him. So thank you, Mathieu. And our third talk will be by Zsolt Kramer. Zsolt is a PhD student at Budapest University of Technology and Economics in Hungary, and his main research interests are congestion control in cellular networks and cooperative traffic handling solutions. And Zsolt will be talking about cooperative performance enhancement using quick tunneling in 5G cellular networks. So let's start with the video. Please, Metako.
Hello everyone, my name is Zsolt Kramer. I'm a PhD student from the Budapest University of Technology and Economics, and I'm going to present our paper titled Cooperative Performance Enhancement Using Quick Tunneling in 5G Cellular Networks. The other authors are Mirja Külavin, Markus Ilar, and Attila Mihai from Ericsson. 5G is going to bring very high peak data rates and significantly lower latency. However, the propagation properties of the new radio also result in higher volatility in available bandwidth. Previous studies showed that these factors intensify the need for a shorter control loop and local optimizations in the transport layer. In LTE networks, this has been mostly achieved by performance enhancing proxies, which basically split the end-to-end connection into two separate control loops for the two separate domains. QUIC has recently been standardized as RFC 9000, and it is already widely deployed by Google. It is expected that the traffic share of the protocol is going to increase rapidly after the standardization. It's a fully encrypted transport protocol, achieving an enhanced privacy for end users. However, this end-to-end encryption also makes connection splitting solutions not feasible anymore. So a new approach is needed to enable network-assisted performance optimization for encrypted protocols. What we propose is a cooperative performance enhancement framework using MASC as the signaling protocol towards the proxy, resulting in two layers of connections, a quick tunnel between the client and the proxy, and the end-to-end quick connection between the client and the target application server. It is important to note that the security context of the end-to-end connection is unmodified, so confidentiality, source authentication, and integrity is preserved. Explicit consent is required for requesting a service from the proxy. And the separation of communication channel data and tunnel data is possible by maintaining separate quick streams in the same quick connection. Overall, this design proves that it is possible to provide proxy services without violating the end-to-end principle of the transport and application layers. We have identified 3 different use cases based on a different granularity of cooperation between the server, the client, and the proxy. And these are local loss recovery, promise signaling, and sending declarative messages to the server. When the client requests the local loss recovery feature, it is done by using the reliable data stream service of the quick tunnel. And besides this initial explicit request, no additional signaling is needed. Although packet losses are considered rare in 4G and 5G networks when using acknowledge mode, this use case can improve the performance of unacknowledged mode as well, and thus enable lower latency. On the right, you can see some preliminary performance results using 1% emulated random loss. And you can see that the average download time is significantly lower when the local loss recovery feature of the proxy is used, especially if the RTT increases. Promise signaling is useful if the bottleneck is between the client and the proxy. The proxy is able to send a so-called promise signal, which indicates the reception of a packet by the proxy. And then the client can progressively acknowledge these promised packets to the server. So this allows the proxy to buffer a sufficient number of packets and then quickly send them to the client if the capacity increases. This is similar to how split connection performance enhancing proxies operate today. The third use case is sending declarative messages to the server. This assumes another explicit tunnel between the proxy and the server. And then the proxy is able to send declarative safe to ignore messages containing acknowledgement or even NAC info. And the server can then utilize these acknowledgements and apply a multi-domain congestion control algorithm, which maintains two separate control loops for the wired and the wireless domains. One of them is clocked by the acknowledgements from the proxy, the other one clocked by the acknowledgements from the client. One of them can be more conservative and the other one more aggressive, and thus the algorithm is able to provide both fairness in the wired domain and fast utilization in the wireless domain. On the right, there are some early results using the millimeter wave module of the NS3 simulator, and it can be seen that multi-domain congestion control outperforms cubic significantly, especially if the RTT of the internet link increases, with both using the Codel AQM and the fixed 7 megabyte drop tail buffer. In conclusion, transparent connection splitting performance enhancing proxies are not going to be feasible for encrypted traffic. We have proposed a cooperative performance enhancing framework based on the MASC protocol, built on explicit consensus by the endpoint and maintaining an unmodified security context of the original end-to-end connection. We have shown 3 different use cases: local loss recovery, promise signaling, and declarative messages to the server. Shown some promising early performance results, and our future work mainly focuses on a detailed performance evaluation in 4G and 5G network conditions. Thank you for your attention.
So thank you, Zsolt, for that video presentation, and I will ask you also to turn on your video for the discussions, and you can now join to have your questions for Zsolt. So I see Marcus in the queue, so please, Marcus, you can unmute and ask your question.
Yeah, hello, can you hear me?
Yes.
Yep.
Very good. Very good. I wonder, after seeing the first presentation from today about the nested congestion control effects when it comes to multi-path scheduling, if something like this also applies to this, even if it is single path, to this quick over quick scenario you presented today. Are there scenarios where the overall performance suffers from congestion control over congestion control?
Good question. Thank you. We have not encountered such a thing during this early performance evaluation, but yeah. So basically, that's my answer. We have not encountered such a thing yet.
Okay. If you allow me, I have a second question on this. So far, you tested quick over quick. Is there also the idea to allow in future non-end-to-end protocol, end-to-end protocols which are not quick? So, for example, TCP, which uses other congestion controls than BBR.
I think this framework targets quick explicitly. So what we are aiming to do is provide this cooperative means of performance enhancement, which has become impossible due to the end-to-end encryption. So we are utilizing mask, and if mask is there, and we have these two layers of connections, we have this tunnel, then we want to establish this channel between the client and the proxy, and enable these performance enhancement use cases with this added communication. And this is, I think, a quick specific framework, but the question is still interesting.
Okay, thank you.
Okay, next we have Hisham. You may unmute to ask your question, Hisham.
So thanks for the presentation. Very good ideas. When you said it is based on mask and mask, when I looked at the working group site, you don't have any RFC or any published specification. So I'm not sure when you say it is based on it, what do you mean?
Yes, it's
Subject to the group. I don't know.
It's relatively recent working group, and so what I mean is, for example, the channel between the client and the proxy is established via an extension of the HTTP connect method, and this is very much related to the mask working group. And mask basically describes this framework of having a quick tunnel over the end-to-end quick connection.
Yeah, so when you say based on, you mean using similar idea, right?
Yes, you could say so, but it follows the documents and the design that is being worked on in the mask working group.
Okay, thank you.
Okay, I think we can allow, if you have questions for any of the earlier speakers, you may also join the queue. We have several people still in the queue, so we will take those, but just to open up the floor for joining for questions to everyone. Next is Vidi. Please unmute Vidi and ask your question.
Can you hear me?
Yes.
Okay. So my question is, maybe I missed this during the presentation, but what's the main difference between the multi-domain and cubic?
Okay. I think I heard most of your question. So the main difference is that the multi-domain congestion control algorithm has two components. They are running in parallel, and they are clocked by the different type of acknowledgements. One is the acknowledgement from the client, and the other is the acknowledgement from the proxy. And these control loops, so there are two congestion window state variables maintained, and these are clocked in parallel, and then the algorithm selects the lower one of the two. So thus, it is able to adapt to the location of the bottleneck. And if the bottleneck is in the wireless domain, then it can behave more aggressively because resource sharing in the mobile network is not the responsibility of the congestion control algorithm. It is taken care of in lower layers. And if the bottleneck is in the wired domain, so let's say the internet, then it behaves similar to cubic, like cubic with a lower RTT. I hope I answered your question.
Can you hear me?
Yes.
Okay. So you said the algorithm is same, but it's just the acknowledgements are coming earlier from the proxy. That's the main difference?
If the bottleneck is in the wired domain,
Right.
then yes. Yeah, but in our our measurements, the bottleneck was in the mobile network, and then it's a much more aggressive. It's similar to a scalable TCP, but it's you could use BBR or any kind of algorithm with fast utilization properties.
Okay, thank you.
Thanks.
Okay, next we have Jake. Please unmute and ask your question.
Hi, can you hear me okay? Great. My question is, does this have any automated proxy discovery involved, or is it just a configured proxy?
I think at the time it's pre-configured.
Okay. Are there? I guess that'll be future work. I mean, is that something you're intending to pursue, or just
yes,
sort of?
Or definitely to explore. Yes.
Great. Thank you. Interesting stuff. Thanks.
Next up, we have Tianjie.
Hear me right now? Hello? Hello? Yes, okay.
Yes.
I was reading through your paper, and in the figure you mentioned, okay, you are going to use the proxy. But I checked your words, but I couldn't find where you are going to put the proxy. I saw you mentioned like mmWave for 5G. But the thing here is like, are you going to put the proxy toward like the UPF, the user plane function, in the data path for 5G? Or it's going to, sometimes for a lot of the user cases, the UPF may not be so close to the access network. So if you put that your proxy behind the UPF, or maybe the session, the PSA UPF, so how are you going to handle those the bandwidth, the delay, the latency things? So I couldn't find in your paper.
Yeah, that's a very good question. I think this is going to be a very important part of future work, like get the proper placement of the deployment, and maybe even experiment a little bit with the performance evaluation. The most important thing is that it has to be very close to the border of the wired and the wireless domains. But exactly in which entity of the cellular network, then I think it's still a half open question.
Okay, yeah, I can give you some number like for some mobile provider, and based on the setting, the UPF could be put toward the access side with 5 to 10 hops in terms of the IP hops after the BBU. And for other cases, it can go up to 20 hops for the IP hops. So it is a little bit, for the like, yeah.
Thank you very much, and good question.
Sure, thank you.
So as we have moved into the panel session, maybe Marcus and Mathieu can also turn on your cameras, and when you ask questions, you can tell who the question is for, and also maybe if it's for more than one author. So Hisham, you are up next.
When I looked at the title of the session, it is New IP Protocols. And I don't think any one of, maybe I'm wrong, any one of this presentation describe a new protocol, maybe enhancements to existing ones. So the session title was a little bit confusing to me. Maybe I'm wrong, I don't know. Because I don't see new protocols defined.
So maybe each of the speakers can say what is new about your approach and how it relates to the evolution of the internet in response to Hisham's question. I guess for the naming we have to ask the chairs, but this I think is an interesting panel question for all of you. So maybe Marcus, you can start. We take the free papers.
Okay, so there's no new protocol per se in the work we're doing, although we are working with multipath DCCP, which is a new protocol. What it is a evolution of existing protocols and existing schedulers. So it's not exactly new protocols. I actually agree with that. It's more like maturing protocols or schedulers.
Mathieu? Now we have don't hear you again.
Sorry, again, my fault. Yes, of course, MPTCP is not a new protocol. We are using for MPTCP, as maybe you know, there is a new version, MPTCP v1, but basically it's still MPTCP behind, not a lot of changes, even if they are important. On the other side, we were using a proxy, the zero-RTT convert protocol, which I think was never used in production network, or at least not that I saw. So it's kind of new. So we hope also it will be used. So yeah, that's it for me.
Yeah, and Salt?
Can you hear me? Sorry for the issues with the camera. I'm not sure what's happening. Yeah, so kind of similar answer. Quick is not a new protocol unless you count it as new due to the recent standardization. But the method to provide cooperative performance enhancement with Quick is novel.
Yeah, so in summary, I guess we have in the first session MPDCCP, which is a draft at the moment, so that's clearly maybe a new protocol. And Salt, you have also used MASC, which we had a question about because it's not yet fully defined. So I think this is also new protocols in development in some sense. And Mathieu, you had the zero-RTT convert, which is just became a RFC and, as you said, has not been used before. Maybe we should also point out that I think that at least some of the presentations here also make available these new protocols as open source. So it's also possible for other researchers to build on and experiment with those protocols. So thanks a lot also for this. I don't see any more people in the queue, and we actually are also running out of our time slot. So I think this was a very suitable last question, and maybe after the replies, the name was actually also quite well chosen. So thanks a lot to all the speakers, and also to all the participants for your questions and engagement in the session. And we will continue immediately with the session 2. So I will hand over to the chair for this session, Teresa. So thanks a lot.
Thanks, Anna. Hi, I'm Teresa Enghert, and I will be chairing the practical congestion control session. So for this session, we will have 2 pre-recorded talks, and then each with a short Q&A after, and then we are going to have a panel discussion with both authors at the end. And now our first speaker for this session is Natalie Romo Moreno. Natalie is working at Deutsche Telekom, where she has carried out this research as part of her work on fixed mobile convergence. And she also holds a master's degree in information and communications engineering and a bachelor's degree in electronic engineering. And the pre-recorded talk that we are going to see in a minute is called CCID5, an implementation of the BBR congestion control algorithm for DCCP and its impact over multipath scenarios. So if we can have the recording, please.
Hello, everybody. My name is Natalie Romo, and welcome to the presentation of the paper CCID5, an implementation of the BBR congestion control algorithm for DCCP and its impact over multipath scenarios. This presentation is divided in 4 sections. I'm going to start with an introduction where I explain the motivation and the objective of this research, following with the description of the design, the evaluation, to finalize with the conclusion and the future work. So the multi-connectivity and hybrid access technologies have been an active research topic during the last years, as they enable the simultaneous use of heterogeneous networks, and this brings some advantages like capacity aggregation, reliability, and flexible resource management. Following this interest, many solutions have already been developed, and some of them are already under standardization, like it is the case of the broadband form standard for hybrid access and the ATSSS specification, which first appeared in the release 16 of the 3GPP standard. This specification has already defined a MPTCP as a solution for traffic splitting, but it is limited only to the reliable and in-order transport of traffic, which means it is not suitable for any real-time service or application, and is also not suitable for the transport of quick. On that basis, the MPTCP protocol was developed to provide a multipath solution capable of transport non-reliable traffic. MPTCP extends the datagram congestion control protocol to support multipath sessions. As I said, it provides unreliable transport of data, it is connection-oriented and congestion controlled. In addition, a framework was developed which combines the MPTCP protocol with other functions like scheduling, reordering, and virtual network interfaces to enable the transport of any IP traffic across multiple access networks. This framework has already been tested and evaluated, and the evaluation results show that the latency difference among the paths available has a strong impact on the end-to-end performance. Also, the latency difference has a strong dependence on the congestion control used within the framework. Right now, DCCP has 3 congestion control standardized, which are CCID2, CCID3, and CCID4. And all of them are based on existing TCP loss-based congestion control algorithms. Having all this idea in mind, the target of this research was to improve the MPTCP framework by extending the TCP protocol with a new congestion control algorithm. The algorithm selected was BBR, which was initially developed for TCP, and which has also shown quite good results in terms of maintaining a low latency while achieving a high throughput. BBR defines two conditions to achieve an optimal point of operation. The first condition is that the amount of data in flight has to be equal to the bandwidth delayed product. And the second condition is that the bottleneck packet arrival must match the bottleneck bandwidth. To fulfill these two conditions, BBR initially estimates the values of the bottleneck bandwidth and the round-trip propagation time, to later use these values to calculate three control parameters, which are the congestion window, the pacing rate, and the send quantity. The way these parameters are updated and the way the whole protocol behaves is ruled by this state machine depicted in this figure. In the startup state, the sending rate will increase rapidly until the pipe is detected to be full. Once this detection is made, the sending rate will be reduced to drain any possible queue, to finally go into a probe bandwidth state, where the amount of data in flight is slightly increased from time to time to probe for more available bandwidth. From any of these three states, the algorithm can go to the probe RTT state, where the data in flight is reduced to probe for lower RTTs. We implemented BBR version 1 for TCCP using the congestion control identifier CC85. It was deployed within the Linux kernel version 4.14, and it is also available as open source in a GitHub repository. The development of all the functions related to the state machine and the estimation of the path parameters follow the BBR standards. And we also reuse and adapt the code from the BBR TCP implementation in the Linux kernel. In addition to that, the TCP standard specifies that CCID profile has to define some other aspects like the format of the acknowledgement packets, the timing of their generation, and how they are congestion controlled. All these definitions were taken from the CCID2. That means that we use acknowledgement vectors and also acknowledgement rate. Apart from that, there are many functions which are part of the TCP protocol and not of the TCP, which correspond to the tracking of the packets in flight and also to the acknowledgement generation. These functions were also taken from the CCID2. And we also took some other ideas to verify the application limited periods. Finally, to integrate the congestion control algorithm with the multipath framework, we need to provide some information to the scheduler and reordering functions that I have mentioned before. The information that we provide is congestion window, packets in flight for the schedulers, and RTT estimation for the reordering algorithms. To test this implementation, we use two schedulers from all the list of the schedulers available, which are cheapest path first and round robin. Cheapest path first allocates packets based on a predefined path priority, and round robin alternates packets sending through all the available paths. For the case of the reordering, we use the active fix, which reads packet sequence numbers to verify an order arrival. When a gap is detected, the packets are buffered until the missing packets arrive or until a fixed time expires. Now let's go with the evaluation. The topology used during the evaluation corresponds to this figure. We deploy this topology under a virtual environment and also under a physical environment. And we set up two testing scenarios, a single path where the two hosts are interconnected only through the red line, and the multipath where the hosts are interconnected through all the links available. The metrics that we measure were end-to-end latency and receive throughput. For the single path scenario, we initially compared the behavior of Cubic and BBR for TCP to have a reference baseline to later compare the behavior of CCID2 and CCID5. We set a transmitting sending rate of 50 megabits, and we limited the bandwidth available in the path in the middle of the test. Here in the plots, we can see the results corresponding to the latency and the received throughput for TCP and DCCP. As we can see, after the bandwidth change, both BBR and CCID5 show latencies way lower in comparison to Cubic and CCID2. In the case of the multipath scenario, we did two tests. The initial one was sending UDP traffic. We used a similar scheme to the single path scenario, limiting the bandwidth in the middle of the test. We used the cheapest path first scheduler and the active fixed reordering. Here we can see the latency comparison and also the throughput distribution among the paths for both CCID2 and CCID5 and the aggregated throughput. As we can see here, in the first seconds, the cheapest by first algorithm only sends data through one of the bands, which is the prioritized path. And once the bandwidth is limited, the congestion control algorithm detects this congestion and informs to the scheduler. And at this point, the scheduler starts transmitting through the secondary path. We can see that the CCID5 reacts quite faster than the CCID2, and we can also see that for the CCID2, the primary path remains congested, which leads to higher latencies. In this multipath scenario, we also decided to test TCP traffic, taking into account that this framework should be also capable of transporting quick traffic, and these two protocols have some similar behaviors. So for this test, we didn't set a fixed transmitting rate. We let TCP to send as much as possible, but we limited the bandwidth path to 10 megabits per second. As we can see here, the response in terms of throughput is more or less similar for both CCID2 and CCID5, but CCID5 shows better results in terms of latency. Finally, to conclude all this work, we managed to prove that CCID5 has a clear benefit with respect to CCID2 in the multipath scenario, as in all the cases, it reduces the latency, avoiding head-of-line blocking, and also minimizing the reordering effort. We also managed to implement BBR as a congestion control BBR congestion control as a new CCID for the DCCP protocol, proving that the conceptual background of BBR also works for DCCP. And we also integrated our approach into a multipath access framework that can be applied either to the 5G ATSS context or to the hybrid access scenario. As future work, we intend to make more extensive testing of the algorithm, adding some other variables and constraints like concurrent flows to evaluate fairness, path delay, and packet loss. We also want to implement the BBR version 2 of the algorithm. And we also want to standardize the implementation of BBR for DCCP as a new CCID profile under IETF. That is all for now. Thank you very much for your patience.
Thank you, Natalie, for contributing this pre-recorded talk. And now I invite you to unmute your audio and share your video if you would like. Do we have any questions for Natalie?
Okay. Can you hear me?
Yes, I can hear you.
Okay.
So, oh, Jake has a question.
It working? Okay. Hi, Natalie. Thanks. Did you can you talk more about the reordering buffer, or the ordering buffer that?
Yeah. We have different implementations of the reordering. The most basic one is just do nothing and the packets go through directly to the virtual interface. The second option is the buffer reads the algorithm reads the sequence numbers. If a gap is detected, then the packets are stored until the missing packets arrive or until a fixed timer expires. And the third one is an active adaptive reordering that uses the information of the round trip time that I said the congestion control could provide. And with this information of the round trip time, the timer of the buffer can be adapted actively. So it's not a fixed value anymore.
And did you find differences in the different choices for this? Are those explained in the paper?
No, those are not explained in figure. We just wanted to test in the first place that the integration works, that the algorithm is actually able to read the information that the congestion control provides. But in the first place, the target was just to validate whether we could actually reduce the difference of the latencies.
Okay. Yeah. All right. Thanks. I guess we've seen efforts to do that in layer 2 switching before that were arguably counterproductive. But I was just curious if you're seeing anything different. Thank you.
Right, and we have another question from Gori. There we go. Hi, Gori. Cannot hear you yet.
Yeah, we cannot hear you.
Can you hear me now?
Yes, now.
Excellent. Okay, I was wondering if you came across anything in DCCP which caused you problems, or whether it actually worked out as an interesting way to implement a new congestion controller. What about DCCP?
The main difference between the implementation of TCP and DCCP is that for TCP, all the functions that keep tracks of the packets already exist in the control itself, in the protocol itself, because it is reliable. And all those things are missing, of course, in DCCP. So they have to be implemented either taking some things from the CCID2 profile or just by ourselves. So that's, let's say, the main challenge. And also the there's another some sort of limitation is the fact that we have the measurements in packets and not bytes as in DCCP. So of course it is more adaptive for applications that use a fixed packet size.
Okay, I was just interested to hear you do work with DCCP. So thanks ever so much for your talk.
Sorry, I couldn't hear the last part.
Your audio is gone.
Yeah, it's fine.
I think he was just saying thank you for using DCCP.
Okay.
Okay, and now we have VD.
Can you hear me?
Yes, you're a little bit quiet, but we can hear you.
Yeah, I'm sorry.
That's all right.
Still quiet? Okay.
That's all right.
So question about, so I just Googled about CCP. I haven't read much about it. So I was just curious about, first of all, why did you choose BBR? And then did it give you better performance? I mean, I was looking through the slides, but there's a lot of content, but then is it giving better performance than CCID4 with respect to latency and bandwidth utilization?
First, we choose BBR precisely because of the good results that it has shown on TCP, because it avoids buffer bloat, which means that we will have better results in terms of latency. And second, we only tested against CCID2 because for the Linux kernel implementation, we only have available CCID2 and CCID3. And CCID2 is more or less Reno-based, so we have a baseline to compare also with TCP.
Okay, so CCID is mainly for the UDP-like traffic, right? Not TCP-like traffic. So, like why did you choose BBR? Because I suppose you did answer that question. Yeah, I'll think about it more and read your paper. And thank you for the great presentation.
Okay. Welcome.
All right, thanks, Vidi. And now we have another question from, I hope I'm not pronouncing it wrong, Owish. And then I think afterwards we should move on to the next talk.
Can you hear me?
Yes.
Basically, in continuation of the question by Vidi, you mentioned that you were interested in reducing buffer bloat, and that provoked the question: do you observe much buffer bloat within the data center environment, as opposed to the last mile?
Oof. I'm not really sure. I mean, the tests that we did were like in a closed environment in a laboratory, but I don't think there's bigger buffer bloat in the data center than in the last mile. I think it's the opposite as far as I understand. The capacity in the data center has to be, of the links available is higher than you have right way to home. So, but we didn't test it in a real environment. We tested it into.
I see. Okay. So it was not based on observation of buffer bloat in a particular data center, but rather on a on reasoning that buffer bloat may occur.
Yeah.
Thank you. Thanks.
Thanks. All right, so let's move on to our next presentation, and then towards the end, we will have a panel discussion with both speakers. Thank you, Natalie. And now our next talk is from Thomas, who just finished his PhD at the University of Illinois. Congratulations. And at this university, he has been working on mobile, wireless, and cellular networks, as well as the PCC Proteus congestion control algorithm, which he will be talking about in a bit, and he will be joining Huawei soon. His research interests include high-performance transport layer protocols, optimization in software-defined networking, and his talk is called Towards Greater Scavenger Congestion Control Deployment, Implementations, and Interfaces. So let's see the talk.
Hey, I'm Tom. Today I'm here to share our progress and thoughts on greater internet deployments of scavenger congestion control. It follows our previous work, PCC Proteus from SICOM 2020, where we explore a scavenger priority for internet transport. It is inspired by the surging amount of internet applications, and in the meanwhile, the fair sharing objective in most previous congestion control protocols. Specifically, the applications shown here all require network bandwidth resources to accomplish data transfer. However, their users usually have different timing requirements. For applications with inelastic timing requirements, their data transfer should complete as soon as possible. But there are also elastic timing applications, such as system and software updates. They often run in the background, even oblivious to users if it takes longer time. So when applications of the two kinds compete with each other, we can allocate more bandwidth to those inelastic timing ones, while overall, users of both types are happy with their experience. This is also considered to be the main implementation scenario for a scavenger in current limited literature. Then, on that basis, we think there is another important category of applications, such as online video streaming. They have opportunistic elasticity. To illustrate that, let's look at a motivating example. Here, Alice watches a YouTube movie on her laptop under a wireless router, while a system update is running silently in the background, and Alice does not need any feature in the update anytime soon. Apparently, the video streaming flow may have primary priority, with the update flow being a scavenger, so that Alice may enjoy both higher video quality and no rebuffer. Moreover, an online video has the largest encoding bit rate. Corresponding to that, if the throughput is more than enough to support that best QoE, the video streaming flow can also conditionally lower its priority to scavenger. And furthermore, when Alice's video playback buffer is almost full, the risk of having a rebuffer is relatively low. And in that case, the streaming flow can opportunistically switch to scavenger priority for a short time period. In both cases, the update flow runs faster without impacting video QoE. In practice, this may become even more valuable because the competing traffic might not just be a software update. There might be, for example, a second video flow trying to start quickly. That said, by enabling flexible and dynamic switch between the scavenger and primary priorities, we can further extend the scavenger use cases and increase the network-wide utility. Therefore, in our recent work, we propose PCC Proteus. In summary, it is based on the PCC utility framework, where each priority corresponds to a dedicated utility function. Then, with the modular architecture, all the priorities are contained in the utility module and share the same rate control algorithm. Therefore, the scavenger and primary priorities are implemented in the same protocol. That inherently enables PCC Proteus to support dynamic priority switch. However, several factors are restricting larger scale deployments of scavenger congestion control. From the perspective of implementation, the existing scavenger protocols have limited availability, especially in widely deployed transport data paths, such as Linux kernel and Quick. To be detailed, the uTorrent implementation of LabBat is limited to the application itself. The LabBat++ implementation on Windows Server is not open source. Our PCC Proteus is previously tested with UDT, which is not even deployed in practice. More importantly, previous scavengers, such as LabBat, are implemented differently, separate from primary protocols, making it non-trivial to enforce opportunistic priority switch. So in this work, we first push forward the open source implementations of scavenger protocols. We port PCC Proteus to Quick, which is becoming increasingly popular with the IETF standardization progress. And for convenience of academia research and performance measurement, we also provide our own LabBat++ implementation by branching off the uTorrent LabBat codebase. For benchmarking purpose, we compare the impact of LabBat, LabBat++, and the Proteus Quick Scavenger to BBR and Cubic using a combination of mahi-mahi bottleneck setups. The figure presents the CDF of primary flow throughput ratio. When the primary flow uses BBR, we can say LabBat++ does have improved performance compared with LabBat, and it is even similar to our Quick Proteus Scavenger. But for Cubic, a Cubic flow achieves 5.6% higher throughput, competing with Proteus Quick than with LabBat++. In addition, to accommodate the dynamic priority switch with real applications, we envision an interface between application and a transport data path. Specifically, these are the existing common interfaces for congestion control implementation. The congestion controller observes packet reception results based on the received ACKs and instances of retransmission timeouts, and enforce different pacing rates or congestion windows to the network interface card. However, throughout the above process, the congestion controller is oblivious to actual application requirements, which are necessary to determine the appropriate transport priority. So we claim that to convey such application requirements, another interface between the application and transport data path is needed. When deploying scavenger congestion control, this interface is responsible for priority control, including two tasks: priority selection and priority switch. The first task, priority selection, is to inform the congestion controller which priority to use in real time. There are several different ways to implement that with the application transport interface. First, a priority controller can be contained within the congestion control protocol. It takes the input of real-time QoE through the interface and outputs the selective priority. Or the priority controller can be implemented together with the application. For example, when designing adaptive bit rate algorithm in video streaming, the developer can directly determine the priority to use besides the video bitrate selection. In this case, the app transport interface will be used for explicit priority notification. Next, with the dynamically selected transport priorities, the congestion controller needs to switch between scavenger and primary. And this is easy for our PCC Proteus, because as we mentioned, different priorities in Proteus are simply different function APIs under the same protocol. Thus, it only needs a binary flag to determine which function API to call. In comparison, the priority switch is not as convenient if the scavenger protocols are separately implemented from the primary protocols, like the case of LabBat. But we think it is possible to leverage multipath transport as a workaround. As shown here, the sender can use different subpaths specific to primary and scavenger priorities, respectively. it can then direct traffic to one of the subpaths according to the selected priority. And ultimately, we hope the scavenger congestion control can attract more interest so that our envisioned priority control based on the interface between application and transport data path could be accepted or implemented in practice. And the corresponding implementation will also be an important future work. Due to limited time, that's all I want to present here. And thank you all for listening. We definitely look forward to questions, suggestions, and criticisms. Thanks.
Thanks for this pre-recorded talk. And Tom, if you would like to join audio and video. Does anybody have any questions for this particular talk so far? Yeah, I can hear you. Okay, if there's no questions so far, I have a question. Oh, we do have actually a question. All right, Wish, please go ahead.
Can you hear me?
Yes.
Yes.
I have a question regarding the that second control channel between the application and the transport. It suggests that the application should explicitly prioritize the. Okay, my question is, what are your thoughts on a potential situation where multiple applications are claiming that their use case has the highest priority, and thus leading to some kind of tragedy of the commons, where everybody wants the highest priority, but nobody can get any prioritization. I wonder specifically about the interaction between the application and the transport. Thank you.
Yeah, cool. So that is definitely a valid question, and we do receive similar questions a lot previously. So the simple answer to that is, in the case that everyone wants high priority, then that's basically the same case with the current congestion control protocol implementation. Like everyone use either like BBR or Cubic, just the default data path transport protocol. And therefore, that means in that case, everybody use a higher priority, and which means it is not some obvious implementation scenario for this lower scavenger priority. And the motivation for this scavenger priority is that there should be a chance that some application can lower its priority temporarily to benefit others and without impacting this application itself. So that is when the scavenger priority can be used, like spontaneously by the corresponding flows.
Thanks. Any quick response to that? No. Otherwise, we have Hesham in the queue.
So what the protocol you will use, the application can use to communicate with the controller, with the congestion controller? Do you have some protocols in mind?
Yeah, so for that part, it is currently future work for us. Like right now, did you ask the protocol for which part?
No, what protocol or API the application use to communicate with the congestion controller?
Yeah. So yeah, if I understand correctly. So right now, that is future work for us. Like this is a Lightning paper, and we talk about the envision for or our thoughts on this interface. And as you can see, we provide the quick implementation for our priority control, the congestion control protocols. And in that case, then right now there should be some communication for like transport statistics from the lower layer to the higher layer, and then since the quick is implemented in user space, and then for this API, we envision that there should be some communication within from the application layer to the quick transport quick congestion control part, and I think for implementation, some thoughts here specific to the quick data path is that within a quick connection or even lower layer to the quick SYN algorithm interface, there should be some function APIs there. For example, called a priority selection or priority switch, and then the higher level, the application layer, or somewhere between the application and the transport layer, when they convey the application requirements, they can use these function APIs.
But what if several applications request high priority, which will cause congestion to the high priority queue? How you decide which one should be granted this high priority?
So by high priority, it's just the currently default congestion control priority, and if there is like no such APIs, then by default most applications currently use high priority, and we just want to use these interfaces to tell the transport data path when you can switch to lower priority, and then when to switch back. And this determination happened per flow. So there is no, so if for each flow for a specific application, it does not need to know the other, know the choice of the other competing applications in the network or at the same endpoint.
All right, thanks. So now we have Tianji in the queue, and I also invite Natalie to join the video again, so we can have questions to both speakers.
Okay. Okay. Just check. Okay.
Yeah.
It's good work and also very interesting. You know, recently we are working the 3GPP, the tactile and the multimodality communication service. So basically means like for the tactile, the TAC-MM, it's going to have the multiple input sources. Like it can consist of like a video, audio, ambient sensor, and the haptic, like some gesture things. So now, yeah, you know, I'm trying to think. You know, there are some issues regarding the signalization or compete even among all the multimodality input. So here you just answered the previous question, say, okay, well, each flow is going to behave or do something based on its own decision. But for the TAC-MM service, actually, a composite flow is going to include multiple input resources, and with different, like something to be elastic, something inelastic, or something maybe opportunistic as you define or categorized. So I'm thinking how, well, it's not like specific for your work, but try to think, well, from your side, how can we do something, you know, by using your things for the 3GPP TAC-MM service. So yeah, thank you.
Sure. Thanks for the question. So personally, I'm not quite familiar with the 3GPP details, but I think so. For example, in our work, we base the priority selection and switch only on the real-time performance for the flow itself. But if we can like achieve more information on like competitors, and then like we can some more centralized design may be necessary for scheduling and resource allocation. In addition to this only end-to-end based approach, and in that case, in our case, the selection of the priority should be based on one rule, which is the change or specifically to the lower priority selection should not impact the flow itself, but creates the opportunity that if some competing flows within the network can acquire higher bandwidth allocation. And in the scenarios when there are multiple services, as mentioned by you, then so first we may have more priorities instead of only one primary and one scavenger. And also, if we have more inputs in addition to the performance of the flow itself, then we can leverage that either by still by per flow, but with more information, or we if it is possible, we can do some network-wide or centralized control.
Okay. Yeah. By the way, for the CAC-MM, the communication service, among the multi-modality inputs, they are not competing. Actually, they need synchronization and coordination in order to provide the service. So yeah. So just for you.
On that front, thanks for the clarification. So on that front, I think there could be separate priority determination for each of those sub-services. Like for audio, then we can fix it to the default or primary priorities all the time. And for video, there may for video parts, then if the bandwidth is high enough, then this is the most intuitive situation. Then we can switch to lower priority for this video streaming flow when the highest bit rates or is rendered smoothly, or the local playback buffer for online videos case instead of real-time streaming. Then the local playback buffer is heavily occupied, so it is there is low risk for rebuffering.
Thank you.
Okay, do we have more questions for Natalie or for both our speakers? Hisham, please.
This are we implementing all of this across the entire internet? Because the internet is huge and it's getting bigger and bigger every day. So all these discussions we had today and are related to the whole internet, or maybe subset of it, or some limited domains, or some private networks, enterprises. What is the scope where all these things we discussed today are applied?
Thank you for this question. I think this is a great question for maybe both our speakers. Natalie, would you like to start?
Yes, of course. Well, starting from our research, the MPTCCP protocol is attempted to be standardized in IETF, so it's attempted to be a part of the whole internet as well. And regarding to the congestion control that we implemented during this research, we have already some prototypes that work within the public internet with some fixes like some converters to avoid middle boxes problems, but in theory, yes, it is intended to work within the whole internet, not just for private networks or something like that.
Yeah, so in our case, there are two parts in our plans or what we already achieved. So first part is the implementation of the congestion control protocol itself, and just to provide the scavenger priority. And for that part, we currently have open source quick implementation, which we expect to be used by every internet users. And besides that, we have some which is not mentioned in our paper summation, we have some closed source Linux kernel implementation, which already have some real world internet users. And the other part is the interface. So this is future envision in our discussion. And right now, the most available transport protocol implementation is based on the Quick framework. So at least we expect the very next step is to implement these APIs within the Quick framework, which is in the user space. So it should be easier to implement. And we have some collaboration with like industry companies right now, which we hope that can help us if we want to make this interface discussion to be some IETF standards.
Thank you. And unfortunately, we are already at time. So I would like to thank our speakers again, as well as everybody who contributed questions in the chat or to the session, as well as our chairs for ANRW. Hope to see you all tomorrow.
Sure. Thank you.
Thanks.